This lesson is for Chapter 6, Section 5. Open up your notebooks to your next available spot, and your textbooks need to be open to page 466, and we'll get this started. So solutions to inequalities are different than solutions to equation systems or equations. Inequalities are going to have regions of correct answers. If you guys remember in the past, when you graphed a less than or greater than inequality, you had to shade where all of the solutions lie rather than simply putting the graph onto the plane. When you're graphing, a couple things to remember. If you see a less than or greater than in the problem, your lines or curves are going to be dotted because the solutions will not begin on the graph itself. It will be either inside or outside of the graph, and the dotted line tells us that. If you have the less than equal to or greater than equal to sign, then you have a solid line or curve because the solutions do begin with the line itself. And lastly, solution areas are shaded. Don't forget when you are solving, all right, a lot of times you're going to have to take the system that they get you, or you take the inequalities in the system and rearrange them so that they are in graphing or y equals mx plus b form. If you ever divide or multiply by a negative amount in any of your simplifying processes, don't forget to turn around the inequality symbol. All right, so if we were going to take a look at checkpoint problem number 1, so I'm at the bottom of page bottom page 466. If we're looking at this inequality, most of you in looking at this should notice that we're looking at a circle. The radius, of course, is r squared over on the other side. So in looking at this, we should know that our radius is going to be 4. And our center, remember, is h and k. Okay, so if x minus h is in the first parenthesis and I see a plus 2 in there, h must be negative 2 and k must be positive 2. So negative 2, 2 is my center. It has a radius of 4. So what I do is make a mark 4 up, left, down, and right from that center. And then I kind of try to freehand my circle in. Now notice that you had a less than symbol, so your circle is going to be dotted. Now, last thing that you need to do is determine, are my solutions going to be inside the curve or outside of the curve? So what I tend to do is I use a test point. Pick any point that is inside the circle. If it tests and gives us a true solution, it's part of the solution set and we shade it. If it doesn't work out, then it cannot be a solution and we shade around it. So I look at that circle and I love to use the point 0, 0 whenever I can. 0, 0 is inside that circle. So if I put 0 in for x, I'm going to get 2 squared. If I put 0 in for y, I'm going to get negative 2 squared. And if I simplify, I get 8 is less than 16, which is true. So 0, 0 worked, which means my solutions must be located inside that circle. Checkpoint number 2, sketch x is greater than or equal to 3. Now remember these equations or inequalities that have just the one variable, these are going to be your horizontal or vertical lines. So if x is greater than or equal to 3, first I need to graph the line x equals 3. So here's the easiest spot where x is 3. And here's where everybody makes a mistake if they're going to. Where do I go horizontal or vertical from there? Well, try a spot above or below first. Does x still equal 3 right there? Does x still equal 3 right there? And they do. What about if I went off in front of it? Okay, that's no longer an x equals 3 spot, so I know I'm not going to go horizontal, I'm going to go with vertical. Now I go back to my symbol so I know whether I'm doing dotted or solid. It's a greater than or equal to symbol, so it is going to be a solid line coming through 3. And now I need to figure out where to shade my solutions. If x is greater than or equal to 3, my solutions are bigger than that, so they are going to shade to the right of the line. This one, we're getting a little bit bigger, a little bit more to it. There are two variables in this, so with nothing being squared, I know I'm going to end up graphing a line. The easiest way to do this for me is y equals mx plus b. So this value, if I'm going to get it here to this setup, that's on the wrong side. So if I move something to the other side of the equal sign or the inequality sign, remember to change the sign of the term. So leave the positive y where it's at. X to the other side becomes negative x. And then minus 2 or negative 2 is going to stay where it was. So in this graph, b is equal to negative 2. So my intercept is negative 2. Go ahead and graph it. My slope is negative 1, or rise over run form, negative 1 over 1, which means down 1, right 1. We'll just make a bunch of them. You could also go up 1 and left 1 if you wish. Taking a look at my symbol again, it's going to be a dotted line. So the graph of my line goes there. Now again, I need to figure out where my shaded solutions are going to sit. I can pick 0, 0 again because it is not part of my line. 0, 0 falls to the kind of the rightish side. If I put 0 in for y and 0 in for x, I'm looking at the statement 0 is greater than negative 2. 0 is greater than a negative number, so that 0, 0 test point works as a solution. So I can shade everything that's on the side of my line with 0, 0. Systems of inequalities can also be graphed, and the mutual shaded region is the solution that you're looking for. So when we put a couple of lines up, we're going to look for where they cross, but more than that, we're going to look at where their shaded regions cross. All right, so checkpoint problem number 4 gives us an example like this. So each of these lines need to be graphed on my grid. So first thing that I'm going to do is I'm going to rewrite them all in y equals mx plus b form. All right, so I'm going to move x to the other side. I will end up with y greater than or equal to negative x plus 1 then. My second line, same thing. I have a negative x on the left. I want my x term to be on the right. So that one's going to turn into y is greater than or equal to positive x plus 1. And then y is less than or equal to 2 is ready to go. All right, so my first line up there has a intercept of 1 and a slope of negative 1. So at 1, I'll put a dot. And from there, I'm going to go down 1, right 1. My symbol is greater than or equal to, so that's going to make a solid line. Doing a test point. Notice how 0, 0 is underneath the line. I'm going to use it still as my test point, and if I put it in, I get 0 greater than or equal to 0 plus 1. So is 0 greater than or equal to 1? And the answer to that is no. So I'm going to shade the other side, not the side that has 0, 0 part of it. Now, with changing to another line, I'm going to change to another color pen. You guys, when you have just a pencil to work with, you could either use a pen to do one of the lines if you feel confident enough with your graphing skills. Otherwise, when you're shading, just shade your lines in a different direction. So like if you shaded like I did on this one where the lines are kind of sort of horizontal, after you graph the next one, maybe you want to do your shading with vertical lines instead. And then you'll be able to see where the overlap part lies. Okay, so ready to graph. B is again 1. So it'll start at the same spot. But now on this one, my slope is positive 1. So I'm going to go up 1, right 1. My symbol tells me, again, it's going to be a solid line. Picking a test point to shade. 0, 0 is kind of under and to the right of my green line, so I'm going to use it again as a test point. It doesn't cross through 0, 0, so I'm safe. 0 greater than or equal to 1 is false. I again do not want to include 0, 0 where I shade my green, so I'm going to the other side of the line. My final line to graph is y less than or equal to 2. My y equals 2 line is right here. If it's going to be less than or equal to 2, I'm going to graph underneath. So my solution is this small little triangular area where red, blue, and green all ended up being. Now, the last thing that our question asks us to do is to state the vertices of the region. So if you look closely, we have a vertice at 0, 1, another vertice at -1, 2, and another vertice at +1, 2. Okay, so those three vertices frame up that triangle that finds our solution region. Checkpoint number 5. All right, so if you're following sort of kind of along in the book, we are now to page 469. Sketch the solution region for this one. Now, when I look at that top part of my system, I see a squared term. Okay, so if I have a squared term, I know I'm going to end up with a parabola. I'm moving my y squared to the other side. So now I have x is greater than y squared. My other line is there's no squared terms in there, so I know I have another linear equation in my system. So I'm going to move x to the other side. Y is less than -x plus 2 to graph. So both of these need to be graphed on my my problem. One thing that I'm looking at here, hang on. Y squared less than x. No, we're okay. With the parabola, you may want to generate a table of values for there. Remember, with the squared term, you're going to get that mirror effect. So I'm going to pick some y's. I always pick 0. And if I put 0 in, I'm going to get 0. But I'm going to go 1 and -1, and I'm going to go 2 and -2. Because when I square each of those y values that I just picked, I should end up getting the same x value back. So if I put 1 in for y, squaring that will give me 1 back, and so will -1. 2 ends up being 4. -2 also ends up being 4. All right, so a little table of values helps us get this parabola going in the right spot. So graphing, I've got 1, 1, 1, -1, 4, 2, 4, -2. My symbol is a greater than symbol, dotted curve. So even with parabolas, you have to watch for that so you get dotted versus solid lines correct. Now the shading. Again, you want to pick a point either in the curve or out of the curve, doesn't really matter which, to see if it's a solution or not. And if it is, you're going to shade over that point, and if it's not, you're going to shade the other part. 0, 0 is part of your curve this time, so you can't pick the origin to test with. So the point 1, 0 is pretty simple to work with. It's right here. I'm going to go with that one. I'm going to put 1 in for x and 0 in for y. So is 1 greater than 0? Yes, it is. So my solution for my parabola is inside my curve. All right, now I'm going to come back and I'm going to graph my line. My b, or my intercept, is 2, so graph it. My slope is -1. So from there, I'm going to go down 1, right 1, all the way through. My eyes are going buggy as I go through my green there. The symbol, no equal bar, so we're going to do another dotted line. Shading. Pick a point. I can use 0, 0 this time. 0 less than or equal to 0 plus 2. So ask yourself, is 0 less than 2? Sure it is. So my blue shading will use and cover 0, 0. All right, so can you see the spot right in here that had both blue and green. There's the solution to your system. Checkpoint 6, sketch the solution set of this system. No squared terms, so I know both of these are going to end up graphing lines for me. So let's get them in graphing form. Move 2x to the other side. So negative y is less than negative 2x minus 3. I don't want negative y here. I want positive y, so I'm going to divide everything by negative 1. Now remember, way back at the beginning of the PowerPoint, I reminded you guys that if you ever have to multiply or divide by a negative value, you have to turn around the inequality system symbol. Okay, so turn your less than to a greater than. All right, next line we're going to do the same thing. Move 2x. We've got negative y greater than negative 2x plus 1. Divide by negative 1 so that y is positive. And we end up with y is less than 2x minus 1. Because again, with dividing by negative 1, you have to turn that thingy around. All right, graphing. B is 3 on my first one. Plot it. M is 2. So from there, up to right 1, up to right 1. Dotted line. Shading on this one. Doesn't go through the origin, so I can use it. Is 0 greater than 2 times 0 plus 3? Or in other words, is 0 greater than 3? No. So don't shade where the origin is. Go the other side of the line. My next line. B is negative 1. Plot it. Slope is 2. Up 2 over 1 again. Dotted line again based on the symbol. Pick a point to test. Put that there. I can use 0, 0 again because believe it or not, even though my line's a little bit messy, it does not go through the origin. 0 less than negative 1. 0 is less than negative 1. No, it's not. 0 is greater than negative 1. Don't do the side with the origin. Go over here. All right, now, looking at this system, are there any areas that got shaded with blue and green? And the answer to that is no. So for this system, without that overlap of the shaded regions, we have no solution for our system. All right, number 7. We're almost there. We've got just a couple more things to go over. Example number 7 is found at the bottom of page 470. Again, it's checkpoint number 7. Sketch the solution set of this system. On that top line there, I think you guys will recognize that we're going to have another parabola with that. So I'm going to keep y where it's at, move x squared to the other side. I don't want a negative y. So divide both by negative 1. Switch your symbol around when you divide by negative 1, and that one will be ready to go. My next system, move x to the other side. Divide everything by negative 1. Turn around your symbol because you are dividing by negative 1. And now we're ready to graph. Again, if you need to, many of you guys are going to recognize that this is just that parent function parabola. So if you remember and you want to just go ahead and graph those points, otherwise make your table of points, you'll find them again. Look at this one and ask if it's going to be dotted or solid. Hopefully, again, you said dotted. Test it with a point. It uses 0, 0 in the graph again, so I can't use the origin. So maybe I'll just go up here to point 0, 2. If I put 0 in for x and 2 in for y, I end up with 2 is greater than 0, which is true. So my shade for my green curve is going to be inside my parabola. Now I'm going to graph my other one. B is 2. Plot it. Slope is 1. Use it. Dotted line again. Test point. We can use the origin. Our line did not cross through it. Is 0 greater than 2? No. So we're going to be shading above. Now with this one, a little bit different than that other one where we had crisscrossed curves and whatnot, or crisscross lines. This one does not have an end. Do you see how this is going to go without bound into infinity as far as that curve will extend? So everything, I'll use the red, everything that blue and green is, so essentially it's going to be everything that's inside our parabola curve forever. Okay, that's going to keep on going here, right? So everything in here, it's going to have solutions without bound. There's an infinite number of them. Now, one area where systems of inequalities are used, all right, you guys always ask, when am I ever going to use this stuff? Well, when you're determining supply and demand, a company can determine where these, if they can determine where these two things meet, they can maximize their profits and efficiency. So computers, I would have to say, safely do this for them in the majority of situations, but it is one of those real life situations where, you know, if you're running a business, you want to know how many of your product are desired, because if you produce a whole lot that never get purchased, you lose money. If people want more than you produce, you're going to lose out on money because you could have sold more. So you want to know where supply meets demand. All right, so checkpoint number 8 gives us one of these situations. Example 8 in the book does as well. It gives us these two price equations. The demand and supply equations for flat screen TVs are given. Okay, so what we're going to do with these first is we're going to rearrange them so that we can graph them. Actually, these are in y equals mx plus b form already. So if we were, well, sort of, I guess I am going to move it a little bit. Let's make it graphable. Usually, or always, the x term is our slope term, so I'm just going to move this little guy over and put my constant at the end. I'm going to do the same thing with this one. Now, I didn't use a pre-done grid paper because these numbers are huge and my slopes are very small. So we're going to do a little bit of estimating while we're graphing. Okay, so beating my first intercept up there is 567. I'm just going to number by hundreds. And I got to get up here to about 600. So 567 is going to be roughly here. Now that slope is very, very slight. So it's what, tens, hundreds, thousands, 100 thousandths, 200 thousandths it is. So where in the world are we going to end up finding an intersection of these two lines with a slope like that? All right, so here's where we use what we've been using throughout this chapter to help us figure out that intersection point. All right, so I know that this is that, and I know my other intercept, let's see, 1, 2, 3, 492 is going to be right about here. But using that kind of a slope is pretty rough. So let's do this with a system. I'm going to send a -1 through my top equation. So I can eliminate P. So putting these together, P's are gone. Going to get 0.1, 2, 3, 4, 5x. And negative, what do we get there? 75. Move 75 to the other side. Now positive 75 is equal to 0.00005x. Divide both sides by 0.00005. And we're going to get Oops, got crazy with the comma. Okay, now we can use that to find our y. So we can find the point where these two lines would intersect. So it doesn't matter where, or I shouldn't say solve for y. In this case, it's going to be solving for p. I'm going to put this into that one. So p is equal to 0.00003 times x plus 492. Okay, so p equals, let's see, I'm going to grab a calculator. I don't want to screw up a decimal point here. We get a 45 out of that. And we end up getting 537. All right, so what does that mean? That means at 1,500,000, comma, 537, we're going to find a point of intersection. Well, 537 we know is going to be in between those other two intercepts. So let's just pretend that it ends up out here. Obviously, this is not 1.5 million away from the origin, but play along. Okay, so we have these two lines. They're going to meet at that point. Now, when we look at that, if we draw a horizontal here, remember this was 537. If we draw a horizontal here, this was our consumer line, and this was our producer line. Okay, so we have an area in which to work. Your area for your consumer is going to be the area of that. It's kind of a triangle slice if you take a look at it. So if you remember way back, to find those, or that space that's inside that part of our triangle. So I'm talking about this area right now. We can find that with 1/2 base times height. Excuse me. Excuse me. Which is the area for that region. All right, so from here to here, that's the base of your triangle. So you've got from 567 to 537. So we have a length of 30. And we have a height of, it's got to be the 1,500,000, which got us over there. And we have to crunch that out. So we have 15 times 1.5 million. Oops. Comma malfunction again, hang on. Okay. Then we're going to have 492 from 537 for our other one. So let's go after our other region. All right, so 537 down to 492. Oops, 45. Looks like a line of length 45. Yep. So let's do it all again. This time we've got 45 Still going to be the same height of our triangle, same vertical or horizontal line. So we have 0.5 times 45 times 1.5 million. Okay. So if we stay within those dollar ranges, those are P's, okay? That's what they stand to make if they have consumer surplus versus producer surplus. Okay? All right. Got nothing else for you. Here are your last 4 assigned problems that I'm going to give you. 8, 14, 32, 38. Hopefully you guys are all going to watch the video tonight so that you have them walking in class. Otherwise, there will be some time in class to get those finished off. So I will see you in class.